So this is going to be part 2 of Enzymes and Energy. So we left off, we introduced enzymes as biological catalysts. So let's continue with that. So we were looking at what enzymes do. Do you remember what they do? They control what, or they speed up what? What do they speed up? Yeah. Reactions, right? They make reactions happen more quickly. So we're going to talk more about that. We talk about things that can affect how quickly they will work. We say that what they do is they lower the activation energy. So if a reaction requires less energy, it should happen more easily. Okay. Now, I don't really care if you know the different ways they lower the activation energy. I'll show you one. But if I show you this animation, you might get the wrong impression. So I'll show you this one. So here's an example of an enzyme lowering the activation energy. So here's a molecule that fits into this site, which is called the active site. So this is the site where the substrate fits in. And you can see what happens. So this is the bond between the two atoms. And you can see just by looking at it, it looks like the enzyme does something to that bond. It looks like it's stressing it. It's putting some strain on it. And by doing so, it'll probably make it easier to snap it or break it. Now, the problem by showing you this animation is you might think that if I just showed you this one, you might think, well, do enzymes just break things apart? No, because I showed you before, a previous animation, that enzymes could put things together. Okay? So the idea is simple. The idea is enzymes make reactions happen more quickly. Here, this is a reaction where something will break apart. So by straining the bonds, it'll just happen more easily. I don't really care if you know the different ways that enzymes will speed up reactions. Just understand that they lower the activation energy in some way. Okay? All right. So here's a neat little example of an enzyme. This is an enzyme that we'll look at in more detail. So this is called glyceraldehyde 3-dehydrogenase. Typically, enzymes have an ASE ending, not always. So typically, it has an ASE ending, and it tells you what it works on. So this one works on glyceraldehyde, and it tells you a little bit about what it's going to do. It's going to remove hydrogen from it. So if you watch, glyceraldehyde will join with this enzyme, and you can see over time that the molecule gets modified. We will look at this one in glycolysis. Okay? So you can see right now, this molecule is NAD+, so it's positively charged. What happens to that molecule? Look, it has gained a negative charge, an overall negative charge. It's actually gained a hydrogen. So if you go back, it's gained a hydrogen, proton. It's gained a proton and 2 electrons. So what's going on with this molecule? This molecule has become oxidized or reduced. You remember? I talked about this yesterday. So it becomes reduced. It picks up protons and electrons. So this molecule, this is the oxidized version. Oop, I went back. Sorry. What happened here? Okay. This is the reduced version. So if this molecule is being reduced, what's going on with this molecule then? If this molecule over here is being reduced, what's going on with this molecule? Yeah, exactly. Remember, if one thing is undergoing something, then the other thing must be undergoing the opposite, right? We'll look at this one in more detail when we get to glycolysis. Okay? So we're going to come back to this molecule. All right. So enzymes are mostly protein. Not always. Sometimes RNA will act as an enzyme, but the ones that we're going to look at predominantly are protein. So the model that is being used to describe how an enzyme works is called the Induced Fit Model. And I want you to look at why you think it's called the induced fit. So here's a picture of a protein. Okay, here's a protein. This is the molecule that the enzyme works on. It's called the substrate. The substrate fits in the active site, and when it fits in, it induces a change in the shape of the enzyme. That's what's called the induced fit model. Kind of like a glove going on a hand. It used to be called, the way it was described, students, how enzymes work, it was called the lock and key model. What do you think is the problem with lock and key? When you put a key on a lock, does the lock change? Does it change shape? No, it doesn't. So they changed the name of that because they gave students the wrong impression. So it's called the induced fit model because that more accurately describes what's going on with enzymes and substrates. Here's some examples of enzymes. You might recognize some of these. Like, what do you think an enzyme that's a hydrolase does? Do you think it makes bigger molecules, or do you think it splits them up? Yeah, because what does it do? Hydrolysis. And we saw that a hydrolysis reaction is when you add water to something to split it apart. Then we have an enzyme that is maybe involved in oxidation reduction or redox reaction, and we'll see the one that we just showed you is involved in that, the glyceraldehyde 3-phosphate dehydrogenase. That one's involved in that. What do you think an isomerase does? An enzyme that's an isomerase. What word do you see in there? Isomer. So it's an enzyme that converts something into something else that's its isomer, like glucose into what? Fructose, maybe, right? Okay. So an enzyme is most likely going to be a protein. It speeds up a reaction. It lowers the activation energy. It changes shape when it interacts with its substrate. And so we said overall what it does is it speeds up a reaction. It controls it. So if you were measuring a chemical reaction with an enzyme, you would see that it should be faster than without an enzyme. But an enzyme or enzymes can be affected by certain things. So we're going to talk about how reaction rate is affected by an enzyme, and then we'll look at factors that affect the enzyme itself or the reaction rate itself. So let's talk about things that will affect the reaction rate. And then we'll look at this one a little bit more tomorrow, okay? So let's consider a reaction like this. The breakdown of starch into sugar. Okay? That's a reaction. The enzyme that runs that reaction is up here. It's called amylase. So we would expect that with an enzyme, this reaction is going to happen much faster than without. What you're seeing here is how the performance of the enzyme is affected by certain things, or how the reaction rate. Because the performance, you have to measure it. Like how you're measuring this performance. Well, we're going to measure it by the production of sugar, right? The faster you make the sugar from starch, that indicates the reaction is happening more quickly, right? So if I'm measuring this reaction, and I'm seeing that sugar is being produced really slowly from starch, then I know the rate is really slow. If I'm noticing that sugar production is pretty high, then I know the rate is pretty high. So what are the factors that are affecting this rate? Okay? Some will be obvious, like this one. Well, if I have more enzymes, so if I look at my x-axis, and I add more enzymes, I notice that my reaction rate goes up. So if I was measuring sugar production from starch, and I have X amount of enzymes, and I double X amount of enzymes, I make more sugar. If I triple it, I make even more sugar. If I quadruple it, I make even more sugar. Why? Why does the rate go up? Because I have more what? I have more enzymes, right? I have more enzymes working on the starch. That one's pretty obvious. Second one over here, my performance or my rate will go up if I add more substrate. So the enzyme is amylase, the substrate is the starch. The substrate is what the enzyme works on. So what happens is, I have a little bit of starch, I have a lot of enzymes, I make a little bit of sugar, because I only have a little bit of starch. If I have more starch, then I have more sugar, right? And if I add more starch, my rate keeps going up, but you notice it doesn't go up the same way that this one goes up. Now, over here, you have to assume that there's excess substrate. What that means is that the substrate is not a limiting reagent. We don't have to worry about running out of it. Here, the amount of enzyme is fixed. So what we're not changing is the amount of the enzyme. All we're changing here is the amount of the substrate. So you'll see, as we add more starch, the reaction rate goes up, but then it levels off. What happens? Why does it level off? Why does it level off like that? Why does it level off? Can't go any faster. Why? So I'll give you an analogy, okay? Imagine my enzymes are like writers, okay? Writers. And each writer could pump out 1 page per hour. Let's say you're writing a newspaper article. You can pump out 1 page per hour. So let's imagine that the substrate is the paper. I have unlimited amount of paper. So if I have one writer in my team, how many papers will I publish per hour? 1. Because each writer could put out 1 page. If I have 2 writers, 2, 3, 4, 4, 5, 5. If you graph that, you'll get a line, right? You'll get 1, 1, then 2, and then 3, 4. It'll be a straight line. Now, if the paper is the substrate and the enzyme is the writer, what happens in the different scenario? Okay, imagine I have 100 writers, but I only have 1 sheet of paper. What happens? How many papers will I publish in 1 hour? 1. 2? 2. 3? If I have 3 pieces of paper, I'll get 3. Because the other 97 writers are doing what? Nothing. They're nothing to work on, right? Well, what happens though, at some point, you can give the writers 1,000 sheets of paper. But if you only have 100 writers, how many articles or pages will you publish per hour? 100. So at some point, the writers, like the enzymes, can't go any faster. They just can't go any faster. So they level off. Okay? They level off. And that's why you get this over here. So when you're measuring the reaction rate, these are just some things to consider. Increasing the enzyme will increase the rate, and that's linear, assuming the substrate isn't, not limiting the reaction. Increasing the substrate will increase the rate, but to a point. Okay? Here in this graph over here, this is actually a combination of those two ideas. You'll notice here, what's the x-axis? Substrate. So you see the curve, right? We could increase the substrates, and at some point, you just can't go any faster. But if we add more enzymes, then what happens? The rate goes up. Because we have more things working on the substrate. So one thing to consider is, when you're measuring the reaction rate, the amount of enzymes, the amount of the substrate. Other things, temperature. Let's look at this one over here. All right? What do you notice about the reaction rate? So here what we're doing is we're measuring a reaction rate. This could be the breakdown of sugar. Could be anything, right? In a human. And so the amount of enzyme is fixed, the amount of substrate is fixed. What's different is the temperature. What does the pattern look like? What do you see? So the rate goes up, You can see it going up on this side. And then it goes what? Then it goes down. And at some point we get what's called the optimal temperature, the peak. Now let's look at the first part. Why does it go up? Why does the rate go up? If you're measuring a breakdown of starch in the human body, temperature went up, the rate would go up. Why? How come? You learned about this in grade 9. When molecules are heated, they move more what? They move more quickly. Don't say more faster, that's bad English. They move more quickly. And for an enzyme to work, what does it have to do? What does an enzyme have to do for it to work? Where's the... What does an enzyme have to do for it to work? It has to collide with what? Substrate. It has to literally collide with it. So what happens if the molecules move more quickly? If the blue and red molecules move around more quickly, then what would you expect? Right, you get faster, you get more collisions because the molecules are moving more quickly. Then why does it go down then? Because if the temperature continues to go up, why does the reaction rate go down? Doesn't make any sense. They're moving more quickly. Why does the rate go down? Well, remember, what is this thing? What's it made of? What is it? It's a protein, right? And it's held together by bonds. And what you're seeing here is that an enzyme fits its substrate really nicely, like a hand in a glove. So what happens then if you heat the enzyme? You know the bonds that hold it together? They might start being affected. And as they're being affected, the shape of the enzyme starts to change. And then what you might get is you might get a scenario where the protein shape does not fit the substrate nicely anymore. So you might get more collisions. But what happens is because the protein shape has been altered so much, a lot of those collisions don't work. So what you're seeing on this side is you're getting more collisions, but the shape of the protein has been altered so that the substrate does not fit the protein nicely anymore. So often what happens, the substrate will just slide in, slide back out. So you're getting more collisions, but they're less effective. At some point, if it's really hot, the enzyme has totally unraveled, and at that point, we say that the enzyme has been denatured. Okay? So when an enzyme is denatured, or a protein is denatured, that means it's totally unraveled and no longer effective. Remember, going back to like a protein shape is really important. Changes shape, changes function. What do you notice about the optimal temperature of this enzyme? Where is it? Where does this sit? What temperature here? Yeah, it's like 35, 36, 37. You think that's coincidence? What's the average human body temperature? 35, 36. What should be 36, 37, right? It's not a coincidence, okay? This enzyme, enzymes in your body have evolved to work at the optimal temperature, which perfectly matches the temperature of the human body. If you look at a different organism, like this one over here, this organism has evolved in a different environment, so its enzymes have a different optimal temperature. If you have an enzyme, if you have an organism that evolved in a really hot environment, you expect that the optimal temperature for those enzymes should be higher. And you can see it. Much higher. So this organism lives in a much warmer environment. That's why it's shifted. But look, the overall pattern is what? It's the same. It's the same. By the way, this explains why I remember watching this python hunters a long time ago, and they were looking for, I don't know, this is a big problem with big snakes in Florida. Okay, people take them as pets illegally, and then they get too big and they get rid of them. And they were looking for this big mama, okay, this big scary snake, and they said in the show that we're gonna go tomorrow to go look for her because tomorrow is gonna be really cold. Now, why would you go look for a big scary snake when it's really cold? Yeah, when they're cold, they're not so much as dormant, but they are very what? Slow, sluggish. They don't really move a lot. Now, why is that? Well, a snake, unlike us, does not control its body temperature. So even though it's cold outside for us, we have things that will allow us to maintain the body temperature, right? I mean, you should still wear good clothing, right? But put a snake outside, and if it's cold, you could expect the snake's temperature to drop significantly. Now, what does this have to do with, why is this one man talking about snakes now? Okay. Well, how does an organism make energy? Through the breakdown of what? Food, right? What controls that reaction? What controls that reaction? What controls any reaction in your body? What are we studying? Enzymes. What happens then if we're measuring the rate of reaction, and you can measure the rate of reaction of energy production, ATP production. We're measuring the rate of reaction of ATP production, and it's really cold. What would that rate look like? Would it be high or slow? High or low? Sorry, high or low? It would be very low. So look, if you have a snake that's outside, it's really cold, the enzymes are going to be working really slowly because the temperature is very low. So guess what that snake is going to have a hard time making? Energy. And if you have very little energy, what are you going to look like? Very active or very sleepy? Very sleepy. Okay, so if you're going to go look for a big scary python, go when it's like freezing. Here we have pH levels, and you can see very similar to temperature. You get the same type of pattern. There's an optimal pH for enzymes. So this is the enzyme pepsin. This is the enzyme trypsin. They have different optimal pHs. But by looking at the enzyme and knowing a little bit about its optimal temperature pH, you can learn a lot. We'll wrap this up. I'm going to ask you one last question after this. Where does pepsin work? How do you know it works in the stomach? Because look at its optimal pH. What is it? It's very low. It's 2. What's the pH of the stomach? It's 2. Logic, right? It'd be logical that the optimal pH of pepsin, which works in the stomach, should match the pH of the stomach. Look at trypsin. Where does trypsin work? Does trypsin work in the stomach? No. If you put it in the stomach, would it work there? No. Now, it's not found in the stomach. Where is it found? What's the name of the organ after the stomach? It's the small what? Small intestine. Okay? So just by looking at what's the optimal value for these for these enzymes, you can learn a lot about the organism and the environment. So last one. So we have, we're going to do something like this tomorrow, okay? We're going to talk about the effects of temperature on germinating. We're going to do beans, though. Okay, beans. All right? So let's look at these two over here, okay? Something is germinating means it's active, it's growing. If it's non-germinating, it means it's dormant. It's not doing much. So let's look at these two. Why does corn, when it's developing at 22 degrees, consume more oxygen, so here's oxygen on the y-axis, than corn germinating at 12 degrees? All right? So we have corn So this is the amount of oxygen we're consuming. So we can see corn at 22 degrees consumes more oxygen than corn at 12 degrees. Why? Why is it working faster?
Warmer.
It's warmer?
Higher.
Right? So it's overall, it's body chemistry, right? When something develops, you have cell division, right? The organism is growing, it's making things, it's converting food into fuel. It's all chemistry. If it's warmer, that's happening what? Faster. An organism that's developing faster needs more what? That requires energy, right? How does an organism make energy? By breaking down food using oxygen. Now, not all organisms need oxygen, and we'll talk about that when we get to cellular respiration. But a plant, we know that plants can make food through sunlight, but when a plant develops from a seed, it's not using photosynthesis. Because guess what it ain't got? It doesn't have leaves. So when a plant's growing, it's using its food. A seed has food in it, so it's using up the food, and it does the same thing that you and I do. It converts food into fuel by using oxygen. So we expect that at warmer temperatures, at a warmer temperature, the chemistry is faster, the breakdown of food is faster, the molecules are moving more quickly, therefore oxygen consumption is faster. Okay? So we're going to stop there and then we'll wrap up enzymes next time. The end.